Welcome to the satellite communication course. Today we will see that depolarization. Depolarization is nothing but a occurs because of a whatever the attenuation and phase shift while transmitting the signal. Because we have the non-spherical raindrops there, so that's why the depolarization occurs. Generally, why we are using that two different types of polarization? Because to increase the capacity of a satellite communication, we are using a two polarization, that is linear polarization we are using, vertical polarization or horizontal polarization. Or we can say that is circular polarization, we can use left-handed or a right-hand circular polarization. Now when we transmit the signal get attenuated and there will be a phase shift occur. And because of that attenuation and a phase shift, so we can say that because of that frequency reuse, so depolarization takes place. Now, there are the two types of a depolarization. One is about a cross polarization discrimination factor, and another one is about a cross polarization isolation. Now, that I and XPD here. Now, how this depolarization takes place? We say that we have one vertical component and one horizontal component. When it is propagating through the depolarizing medium, in a satellite communication, it is nothing but a raindrops there, non-spherical raindrops. So that is nothing but a depolarizing. When it is propagating through it, your signal propagating through depolarizing medium. So due to the depolarization, the vector will be decomposed into a vertical as well as a horizontal component. Means we have this E1 is a vertical component and that will be decomposed into a two component, that will be E11 and a E12. E11 and a E12. Now that E2 is a horizontal component. So E2 will be decomposed into a two component, that is E22 and a E21. So if you see that E1 is a vertical component and that will be decomposed in a E11, that will be in a vertical direction, and a cross polarized vector, that is E12 in a horizontal direction. This we have the E11 here as well as the cross polarization component. Similarly, if you consider that E2 here, this one is a horizontal component. So when it is propagating through the depolarizing medium, so this will be the E22 as well as the E21, E22 and E2. Means E2, when horizontal field vector E2, it is propagating through this depolarizing medium, it will be decomposed because of that depolarization medium into a two component, that will be a copolarized component, that is E22, that will be along with the horizontal direction, and a cross polarized vector, that will be in a E21, that will be in a vertical direction. So now if you see that for the E11, the desired component is E11. Because of the depolarized medium, another component will come, that is a cross polarized component E12. So this E12 component is the undesired component. Similarly, when we are propagating this horizontal direction component, that E22 here, so in that case, we'll get that a desired component E22 and a cross polarized component, that will be a E21 here. Now using this desired component and undesired component, we can find out a cross polarized discrimination factor and a cross polarization isolation factor. So that undesired component when we are propagating a analog signal, in that case, because of that undesired component, crosstalk will occur. And in the case of a digital system, it will increase the BER. So you can say that undesired component BR in a digital system and crosstalk in a analog system. Now from this component, desired component and undesired component, we can find out a cross polarization discrimination factor. So this one is about a cross polarized discrimination factor 1. It is the ratio of the desired component of a polarized wave in the polarized direction. This one is about a desired component. Here we have desired component in the polarization direction to the component in the orthogonal direction, that will be E1 to. So we can say that xpd1 is equal to 20 log of E11, that is desired component, and E12 is a undesired component. So this one is about a E1 is a vertical component. So similarly for the horizontal polarized wave, xpd2 is equal to a 20 log of a desired component E22 by a E21, that is a undesired component. Now we will get that a two term, that is a cross polarized component for the vertical polarized wave, and this one is the cross polarized component for the horizontal polarized wave. Now we can find out another component, that is the cross polarization isolation. This one is the cross polarization isolation. That cross polarization isolation between that vertical and a horizontal polarized wave. And that is defined as the ratio of a copolarized component of the vertical wave to the cross polarized component of the horizontal polarized wave in the vertical direction. So we can write I, that is isolation between, or we can write here, that is the isolation factor, that is the isolation between the vertical and a horizontal polarized wave. Horizontal polarized wave. Now in that case, we can find out the isolation factor, and that will be I1 is equal to what? A 20 log of E11 by E21. This here, this one is a vertical, this one is a horizontal component, and this one is about a, sorry, this E1 is a, here E1 is a vertical component. So we have this isolation between this E1 vertical component, and this one is the E2, and we have a cross polarization component, that is about a E21 of this E2 here. So isolation between these two vertical components, that is E11 desired component of E1, and E21 it is the undesired component of E2. So means we can say that the ratio of a copolarized component of the vertical polarized wave, that is E11, to the cross polarized component of the horizontal polarized wave, it is nothing but what? A ratio of what? This one E1 is what? Is the copolarized component of copolarized vertical component of vertical polarized wave, and E21 it is the cross polarized component of the horizontal polarized wave. Okay, this one is about a, we have the vertical polarized wave component, This one is the component of vertical polarized wave, and this one is about a cross polarized component, cross polarized component of horizontal polarized wave. Horizontal polarized. That is about a I1. So that is about the isolation I1. That will be I1 between the co-polarized component of E11 of the vertical polarized wave and the cross polarized component E21 of the horizontal polarized wave. Then similarly we can find out the I2. That is I2 is the isolation between what? Isolation between the co-polarized component of a E22. Means we can say that a 20 log of a E22 means co-polarized component of a E22 of the vertical polarized wave and a cross polarized component E12 of the horizontal polarized wave. So now we have this E22 component and we say that E12. So now we will get that isolation, that is I1 and I2, that is the co-polarized component E22 here and the cross polarized component E12. So when you transmit a signal get attenuated, attenuation attenuation occurs, as well as there will be changes in the phase shift. But attenuation means the factor means what? A signal reduce, signal degradation, signal level received at the receiver. But in the case of a depolarization loss, so if we increase the transmitting power, so received power can be increased. But in the case of a copolarized component, or you can say the depolarization loss, that cannot be compensated by increasing the power, transmitting power. So how to minimize that, or how we will reduce the depolarization loss? So that depolarization loss, we will use the technique for the reception there. That is nothing but what we can say that we will use the diversity reception and a adaptive compensation of a depolarization. So this way we can reduce, that is about a cross polarization component. Now that is about a depolarization technique here. Another, because of that polarization, phase shift changes. Why this phase shift changes? Because signal is rotating there. When we transmit the signal, when we transmit any signal, when it is propagating through the ionospheric layer, when your signal is propagating through the ionospheric layer, then what happen? So whatever the signal is propagating, so that signal get rotated because the signal is propagating through the ionospheric layer. So that because of that, rotation of this polarized signal will take place because of this ionospheric layer, and that rotation of that polarization signal is called as a Faraday rotation. So Faraday rotation, that will be inversely proportional to the square of the frequency. Faraday rotation is inversely proportional to the square of the frequency. So if you consider that a frequency is about 10 gigahertz, okay, about 10 gigahertz of frequency, there will be a large value of this Faraday rotation. Or you can say that large value means what? A rotation of this polarization signal will be takes place above that 10 gigahertz of frequency. If you consider that a Faraday rotation and a polarization loss, then a polarization loss is equal to what? A 20 log of a Faraday rotation value. This is about a polarization loss. And this value of this Faraday rotation, that will be maximum, that is theta f, that will be maximum, that will be at a 9 degrees at a 4 gigahertz. And maximum, that will be 4 degree at a 6 gigahertz. So that is about a Faraday rotation at a frequency. So generally we say that we are using the linear polarized or a circular polarized signal because of that frequency reuse to counter the effect of a depolarization of a Faraday rotation. We can use a circular polarization. Means we can say that we can use a left hand circular polarized wave or a right hand circular polarized wave. Now, because we say that a linear polarization, that rotation, Faraday rotation, it makes an angle theta something with respect to that particular vector. So that's why we are getting these two components, a co-polarized component and a cross-polarized component. But in the case of a left-hand circular wave, so it is what happened, left-hand circular or a right-hand circular means circular polarization wave. Only there will be a small variation in the angle. This angular shift will be occur, and that angular shift will be occur, and that will be add to the Faraday rotation, overall rotation. So that's why we can prefer the left hand circular polarized wave or a right hand circular polarized. And if you consider that the linear polarized component means vertical polarization or a horizontal polarization, so in that case it has a copolar component and a cross polarized component. Suppose I say that a E1 is a component, so we'll get that a E11 and a E12. That is the copolarized component, and this one is about a cross polarized component. So the instead of vertical and horizontal polarization, we can use a circular polarization. And why this depolarization occur? Because of that raindrops, or you can see that rain or a ice there. Okay, because whatever the rain we say that it has a non-spherical component. It is not a spherical there. So because that rain is not in a spherical symmetry, okay, that raindrop doesn't have a spherical symmetry. So that's why your signal will convert, or there may be a depolarization. That is about a depolarization of a vector. Now next we learn here a propagation, impairment, mitigation technique. Means what we can say that when we transmit a signal from the earth station to the satellite, your signal get attenuated. or we can say that a attenuation or a absorption takes place. Now at the receiver, due to the attenuation or a absorption, so received power level, or we can say that received power level because of that absorption or attenuation will be degraded here. Now then another way is to increase the received power. So we can either we can decrease the level of a reception of a signal, or we can increase the transmitting power. So way means what? Whatever the expected value of a received power will be there, will decrease the level, or we can increase the transmitted power. Now to decrease the reception power level, so then what will happen? Your signal degrades and we are not able to receive the correct value of a signal there. Okay, original signal will not receive. So another way is what? To increase the transmitted power so that whatever the expected carrier to noise ratio at a receiver we will get using this method. Or we have another way, we can increase the gain of the antenna so that your transmitted power will be increased. So that will be both for the uplink and a downlink. Means we can increase the transmitted power means what? We need to increase the effective isotropic radiated power. That is about the EIRP. That EIRP can be increased by using the transmitted power, because EIRP is equal to what? PT into GT. There are the two ways. We can increase the transmitted power or we can increase the gain of a transmitting antenna. And that will be for the uplink and as well as for the downlink signal. So that we can improve the carrier to noise ratio at the receiver. Means we can improve that AC by N ratio. We have the scope is here. Improve the C by N ratio through EIRP. So that EIRP can be increased for the uplink. Uplink means at the earth station. Whatever the EIRP we have, that will be is equal to PT into GT. We can increase the transmitting power and we can increase the gain. Similarly for the downlink at a satellite, we can increase the EIRP, we can increase the transmitting power and a gain of this satellite. Okay, transmitting power at the satellite and gain of the satellite. But at the downlink, that satellite is about a fixed value. Okay, so we can say that for the uplink we can use, can increase this transmit power from the ground station, or you can see the transmit power from the satellite, or increasing the gain of an antenna there. So why we can increase? Because it will improve the carrier to noise ratio. So generally we can say that so power C by N ratio, to get that C by N ratio, constant C by N ratio under a fading condition. So there may be a fade margin of what? A 5 to 10 dB. Fade margin of a 5 to 10 dB. That will be in a K band. Because generally we say that a fade is nothing but of a short duration. So that's why that can be controlled using the transmitting power. Or we can control the transmitting power or a gain, or we can say that we can improve using that, using the EIR. So we have the way to increase the C by N ratio by increasing the uplink power. So we have the mechanism so that it will increase the uplink power so that received power will be increased. If the received power is received, that reduce, okay, we can say that received power to increase, we need to increase the uplink power. If that received power is reduced, that will be reduced due to the signal fading there. That will be occur in the that at the uplink as well as the downlink. So that's why we can say that a signal fade is responsible for the given link. Okay, or we can say that the attenuation in that uplink here. Okay, we can consider here that uplink power control. We have the earth station. That's about a earth station we say, and we will use the duplexer. We have the high power amplifier. Then this one is about a receiver. Then we say that a power detector. Then we have a processor. Then this one is about a power control signal. And this one is about your transmitted signal. Okay. So now this one is transmitting the signal to the earth station, that is up to the satellite. We have the antenna here at the satellite. This one is about a solar panel. This one is about antenna. So you can say that the uplink signal as well as the downlink signal. This one is the uplink and this one is the downlink. But in that region, we say that we have the atmosphere, or we have some particular region. We say that about it. This is about a space here, free space. So attenuation occurs in this particular case. So this one is the method of what? Uplink power control. Because there may be attenuation at the uplink. So we can use this one is about the earth station here. So we can use the a different transmitting antenna for the earth station. So we can increase the transmitted power from the earth station so that whichever the attenuation takes place due to the rain or any other absorption takes place in this ionospheric layers and all. So that's why the received power will be reduced. So if we increase that transmitting power so that we can compensate that attenuation absorption occur in this particular region, so that we can increase the transmitting power, we will compensate it. So for that purpose, we need to know about that how much is the attenuation takes place when we transmit the signal there. So that's why we need to monitor that whether there will be a rain or some that some obstacle in that particular region, raindrops or something else. Okay, that will be occur. So we should know that earth station should know that whether there will be rain or something else occur, so that your we need to increase the transmitting power, because the receiver, that satellite is not able to receive that particular signal. So that's why what happened, that satellite will send one beacon signal. Okay, we can say that we can, to improve this communication or to increase the transmitting signal, then a satellite is to send one beacon signal, and then it will received by the earth station. Then according to that a received signal, then we can say that how much is the attenuation takes place because of the train or absorption takes place. According to that, processor will identify that how much is the correction necessary at the transmitting power. So means how to increase the uplink power, because the beacon signal received by the satellite, or satellite send one beacon signal, satellite send beacon signal to the earth station. So whichever the beacon signals transmitted by the satellite, and that will be received by the earth station. So according to that beacon signal level, so here processor will process that signal level, and according to that a power control signal will be given to this high power amplifier, so that a transmitted power will be increases. So how much is the uplink power is required, that will be processed by the processor, and according to that power transmission will be takes place. So we have the various technique to measure that the whether there will be attenuation takes place in that particular regions or all. So we can consider that adjusting that particular signal, and then we can transmit the power. And that is about the way of increasing the transmitting power. Now this one is about the earth system, means uplink. This is about a uplink power control now. Another way is about the whatever the power received by the satellite on the uplink. Okay, here, and that will be from the telemetry signal. Okay, telemetry signal contains the information or the health of the satellite, as well as the power level at the different points in the transponder there. So then that will decode the information from the received telemetry signal. An accurate control signal can be calculated by the processor for controlling the output of the high power amplifier. So means this one is about a transmitting station. Then a earth station itself, because whichever the signal received by this, by when we transmit the signal, so then we can say that one particular telemetry signal is to be sent to the satellite. Then the satellite will receive that particular signal, and according to that, it will generate a signal, so that that signal will tell you how much is the power is to be transmitted by the earth station. Just like we have the satellite here, it will transmit the signal now. Okay, that will be the signal is to be transmitting a uplink and a downlink now, and that will be received by the earth station. This is about a earth station. Signal will be received by the earth station here, or we get the signal that will be a telemetry receiver. Okay, and according to the telemetry receiver, so we can say that uplink power level how much is the uplink power level is required. So according to that, a processor will process the signal and then it will give the power control signal. So that high power amplification is takes place. This one is about a high power amplifier. Then we have a duplexer, same here, and that duplexer is connected to this antenna earth station. Another method is about here, instead of a beacon signal, you can say that another way to correct that estimate of the power received by the satellite on the uplink, that will be from the telemetry signal. So telemetry signal received contains the information on the health of the satellite as well as the power levels at the different points on the transponder. So that will be decoding or decoded here. That decoding information from the received telemetry signal. So it will generate an accurate control signal that can be calculated by the processor for controlling the output power. So here we can say that in the given region there is the attenuations or something else occur. But when we transmit some particular signal there, so there may be a delay for the received signal because whatever the signal is transmitting from the satellite to the earth station, so that received signal there may be a delay, and because of that delay, so whatever the requirement for the high power control, that processor, so that because of that delay of a received signal, so we could not transmit the signal at that particular instant, or we could not generate that high power at that particular instant because of that delay there. Again, there may be a estimation of the particular signal, or you can say that whatever the detected signal is there, we are not able to detect, or we are not able to accurately detect that particular signal, and there may be a time loop, time delay, or you can say that because of this particular loop there will be a time delay, so that may affect the transmitting power. So that's why we need to consider that while communicating there, whatever the attenuation or absorption takes place in this particular region, so that will be totally depending upon that signal received, that may be delay, there may be a loop delay, or there may be inaccurate concerns of this particular signal strength received there. That is for the uplink. So similarly for the downlink, so same, okay, we can say that for the uplink, so similarly we can use when we transmit the signal from the satellite to the earth station, that is the downlink. So there may be a range attenuation in the downlink also. So we say that increasing the uplink power, it is not a solution only. We need to increase the downlink power also. Means whatever the transponder is present in the satellite, so that transponder is to be operated in a multi-mode, and they will generate a high power, or they may be switched to the two different values, the low power and high power. Whenever the rain attenuation occurs, so in that case transponder is to be generate the high power. So means when the transponder will generate the high power, so means at the transmitting station at the satellite, so we can increase the EIRP. The way for the uplink, we need to increase the EIRP at the earth station. For the downlink signal, we need to increase the EIRP at the satellite. So because of there is a different modes, high power mode and low power mode in a transponder, so that may be easily switched from the low power mode to the high power mode. So switching takes place for the desired EIRP. so that your transponder will generate a high power, or it will transmit the high power signal, so that our station will receive that signal there without attenuation, or whichever the margin is defined by this particular attenuation. So at the receiver downlink signal, okay, because receiver receive the signal, our station receive the signal. So to generate the high power signal at the transponder, so signal will be received with a no attenuation in this particular path there, and that will be occur, or that will be completed by using transmitting the power or increasing the transmitting power at the satellite there. Now next, because we say that increasing the power at the satellite, so effective area of the satellite again we need to increase, because if that EIRP is less because of that attenuation, that EIRP is a small, okay, the transmitting power is small. So if because of that rain attenuation, that coverage area again reduce. If we increase the EIRP, so we can increase the coverage area of the satellite there. So another way is about what we can increase the beam control, because generally what happen, a satellite transmit the signal. If the satellite is work with a multi-beam operation, so multi-beam operation means what? From the satellite, it will be consider this particular region of the area, okay, different coverage area. Like this is about a coverage area of this particular beam. That is nothing but a multi-beam operation. So now, in that case, supposed to be in this region there is no attenuation, and in this region there is the attenuation due to the rain. So in that case, only that particular beam power is to be increased. So if you consider the geographical region or geographical condition, in some particular area there is no rain, or in some particular region there is a rain, and because of that there will be attenuation. So we have, if supposed to be satellite operates in a multi-beam mode, so whichever the affected area or affected region is there, and that region can be switched to an antenna with a narrow beam, that will be providing the high gain. Okay, if we increase, we can say that beam, narrow beam, or that particular region can be covered using the a narrow beam there. And this technique is nothing but what? A beam diversity. So that particular beam, or we can say that is that region or a spot beam antenna that provides a higher gain, and because of that higher gain, that EIRP is higher there. So if you consider that a beam control, so antenna beam width and a gain here. So if you draw a graph of antenna beam width here, okay, half power beam width we say, and that will be in gain in dB, that is 15, 20, 25, 30. You can see here it is about a 50 now. So in that case, and the beam width is about 2, 4, 6, that is in a degree, okay, 8, 10, 12. So here what happened here, that gain is increased. If we use a narrow beam, gain will be higher, and if that half power beam width will be larger, then gain will be decreased. Okay, so we can use a method of a narrow beam, so that the effective isotropic radiated power EIRP will be increasing. Okay, so we'll control the beam width so that we'll get that effective isotropic radiated power EIRP will be higher. So beam width, as I told you earlier, for the given antenna, suppose we can say this about antenna. So this one is a radiation pattern of an antenna. Here we have a maximum here. So 3 dB point here, 3 dB point here. These are the 3 dB point or a half power point, and maximum here. From this maximum to this, these are the 2 3 dB. So this is nothing but what we have the half power beam width. Okay, this one is nothing but the half power beam width. So if this half power beam width will be narrow, so gain will be increased. So if that gain is increased, if we say that a EIRP is equal to what? A PTGT. If it is a narrow beam, the gain increases. So EIRP is increased. So way to increase, instead of increasing the transmitting power, we can increase the gain of an antenna by using the or by creating the narrow beam. Okay. So another way is about the improvement in the satellite signal. You can say it is about a phase diversity. So phase diversity means what? So generally what happens, we say that a rainfall occurs and that will be not a throughout or daily or in a whole day here. So generally rainfall occurs at a particular given time or for a limited duration. So if we consider that if we have the two receivers are placed at a distance, consider that we have the one receiver now, we have the another receiver. We have about the two receivers. You can say that about a satellite. If two receivers are placed at a distance further than the expected rain coverage, then what happens? So signal reaching to the this two receiver now